Good afternoon, everyone. Thank you for joining us today for our webinar, which we have titled as Optimize Your Mold Design and Development Processes. So about our company, we are one of the largest technology solutions providers in India with more than 30 years of business transformation experience. We help transform businesses by enabling the adoption of virtual twin, geospatial analytics, and 3D printing. We have introduced many technologies like AR, VR, digital manufacturing, 3D printing, etc. for the first time to Indian customers. We have established ourselves as a trusted partner for more than 2,000 organizations across various industry verticals such as automotive, aerospace, defense, industrial equipment, mining, and more. We have dedicated regional teams who are reinforced by their domain and functional consultants. We are backed by strategic alliances with global leaders who are pioneers in their respective technology areas. We are also strategic partners to Dassault Systems, whose solution will be discussed by our speaker today, Mr. Shikumar sir. We have a widespread presence with 11 offices across India, with our headquarters being at Bangalore. We are an end-to-end technology solutions provider to our customers. So our speaker for today's webinar is Mr. Shikumar Maganti. He carries a rich experience of more than 24 years spanning technology pre-sales, PLM implementation, project management, on-site consulting services, and technical support. His expertise covers industry segments such as automotive, aerospace, defense, industrial equipment, marine and offshore, and consumer goods. He has worked on-site with prestigious clients such as Ashok Leyland, Daimler, ADA, Cyient, and Tech Mahindra to provide the best customer experience. At TDS Technologies, he serves as Senior General Manager Technical and leads the brand of Dassault Systems 3D Experience, which focuses on digital transformation, Industry 5.0, and sustainability. Over to you, Shikumar sir.
Today's webinar agenda is on optimizing mold tooling design processes, especially for the product development and tool design. And we are going to provide a complete range of solutions from Dassault Systems on mold and tooling design, and how our customers have been using this effective module for delivering their mold designs as well as the tooling processes. I'm going to highlight on this webinar. So today's agenda is on mold and tooling design. I'll start with macro process, how step by step, like how mold makers or the tooling design department, they make use of they go through these processes to arrive at core and cavity extraction, and then the relevant mold tooling, and also like how they're going to utilize this module for their regular activities. Then I will focus on mold and tooling design typical challenges. So what are those challenges that are faced by the customers in the industry? And then I will dwell upon 3D experience criteria mold and tooling designer overview, followed by benefits, and then our customer references across India and the globe. So to start with the macro process, I'll be focusing on the current process, which is a general process basically in the industry. It starts with the preliminary design, wherein you look for mold quality checking, then you look for mold cleaning, then you will also see like the feasibility studies with respect to, say, plastics design, plastic film simulation. Then you will also take care of all those manufacturing constraints like shrinkage and warpage factors. So you run through the plastic flow simulation and understand the feasibility study first as a part of preliminary design, and then you focus on forming surfaces design, which involves core and cavity extraction, then the parting line, parting surface creation, and also if it is having some kind of undercut mechanisms, slides and lifters, and also rest of those elements that come in for a complex mold. And then we also look for some kind of collaborative design changes basically, And then once I complete my core and cavity separation, and then with a clear-cut parting line definition, I move into mold structure design. So this mold structure design focuses on all the relevant elements, like starting with mold base, and then you have cooling systems, mold structure, mold components, and their placement. And also we need to look at the impacts, and then we need to look at deformation injection and cooling simulations. So this is something which is part of mold structure design. And then once we complete that, we move on to mold manufacturing, which involves electrode design, generating bill of materials, and the drawing generation, automated drawing generation. And then we also look into NC programming, that is machining. So this can involve milling, turning, or mill turn applications. And then you complete this mold manufacturing. Then you look into quality control, typically looking at tolerances, probing with the CMM inspection tools, and then mold tryout. So once the tryout is complete, you move into the production planning, that is your regular production with a kind of scheduling in place. So we'll be taking you through this one case study on this preliminary design, forming surfaces, that is core and cavity extractions, mold structure creation, and the mold manufacturing, and followed by quality control and production. So this is the typical process which is followed across the industry, be it automotive or aerospace, or it could be consumer goods, or any plastics based industries. They make use of the similar process flow. So we'll start with like what are those challenges that we may come across during this entire mold design process, and then how we can overcome those challenges using our solution. So if you look at preliminary design, typically OEMs, they provide their component or part drawing, and then they ask us to come out with a mold, and then start working on the prototyping based on this mold and tooling, and then deliver the prototype first, and then once it is confirmed through control plan and PPAP, then you go for production. So typically OEMs provide the data, but they will not look into what kind of complexities are involved with respect to mold design. So that needs to be looked into first. And then it requires a CAE validation at the early stage, because without CAE validation, I will not be able to find out the defects, the shrinkage factors, or what kind of temperature distribution and pressure distribution happening on the specific plastic injection simulation. And then we need to look into those studies first, because without confirming that, we will not be able to move into the next level. So then comes again the core and cavity extraction. Here also there are many changes coming in, and in order to finalize this design, it is going to be a little more time taking. And then we need to look at again the mold structure design as well. So in this regard, again, with respect to the kind of the mechanism, the mold mechanism that runs in, we need to look at how to change these the supporting systems, basically undercuts or slides and lifters, or it could be the cooling circuits. So we need to test and validate all those aspects in the mold structure design. Again, that involves a lot of changes, and also many a time it is more time consuming. If any changes are expected by the OEM or some last minute changes, again the entire the mold base has to go through, the entire mold design has to go through again the same process, so which is going to be time consuming. And then machining is not linked to design typically. So again, that is another challenge which the manufacturers may face. Again, as I said, the bill of materials that needs to be updated from time to time if any changes are made. So these are the typical challenges that you may come across in this entire mold process. And then we can actually overcome these challenges which are coming from the OEM or from the simulation perspective, or it could be from the repetitive nature of the design based on the changes and then automatic updates. So we have a solution to deliver using our mold and tooling designer role on 3D experience platform. So as a part of this mold tooling workflow, we have a set of processes to go through, starting with the plastic filling evaluation. Basically, the plastic filling simulation can be done. You can set the injection points and check how the plastic filling happens across the entire component or assembly. And then once you go through this, you will be able to understand the any kind of shrinkage factors or any other manufacturing constraints. You can virtually validate first with this plastic part manufacturing feasibility assessment. And then once it is completed, you will move into preliminary design. So preliminary design, again, it focuses on, as I said, core and cavity extraction, part lining, parting surface creation, and then accordingly, we need to look at the rest of the mold structure design aspects and all. So here you study all kinds of mechanisms, and then you'll also see what the two structure principles you're going through in this. Then you move into detailed manufacturing simulation. So here you will set up this the cooling circuit, and then you see how this it is impacting the entire core and cavity. And also you can see, I mean, once you set up this, you need to simulate that and see how it is actually helping. Then you need to look at the detailed molded part design. So here you create the parting surface, and then you define all the undercuts, you provide all the compensations of tolerances, and then see how the overall final design looks like. Then you move into detailed mold tool design. Here you will bring in the standard mold bases, and then once you fit in those mold bases, then you can look into all the injection and cooling systems. Then finally you will go for manufacturing preparation, and it can also involve electrode design or NC machining processes. And then finally you will have manufacturing machining assembly, and followed by quality control, and finally the plastic part production. So in this is the typical process through which you're going to go through. I will take you through this example here. So from the 3D experience CATIA mold and tooling designer role, using this you are able to complete all these activities, be it design or simulation, or defining the assembly mechanisms, and then checking the interferences, the draft angles, and then finally going for quality inspection and production. So every aspect is covered using this particular role. And if you look from the typical manufacturing perspective, so the mold and tooling designer, it will go through 6 steps here. I will run you through these steps with the help of a case study. So starting with the initial plastic part evaluation, or the feasibility assessment, we will run through typical plastic filling simulation, which is part of the same workbench, which also involves design as well. So in this example, we are going to take a case study of an engine cover. So engine cover, the plastic part which is highlighted over here, that needs to be brought in, and then we need to look at where are those injection points that I need to define. So this is a typical 3D experience CATIA workbench. So you open the part, and then you look for any duplicate elements. You want to check the surface first, and once the surface is checked, then you will enter into the core and cavity separation application, and there you define the injection points. So in this case, we are defining 2 injection points for this particular engine cover. So once I define these injection points and then mark them here in this particular engine cover, so then I will move into the, I mean, without changing the application interface, I'll straight away enter into the plastic filling simulation workbench. So this is like you are switching between the design to simulation without moving out of the same user interface. So here you define the simulation constraints and then injection locations and the process design, and then you go for the simulation aspect here. So once you run the simulation iteration, you will find like what is the kind of temperature distribution that you have, and what is the filling time that is needed, and what is the pressure distribution, and also what kind of stresses are there, and if any problems are coming in here with respect to this engine cover filling, we will come to know in advance through this virtual validation. So here we have business intelligence essentials, using which we'll be able to find out all the intelligent information. So in this case, you can see volumetric shrinkage analysis, and then you can also see weld lines. You can also see the ease of filling for on the injection lines. Everything can be studied with the help of this particular module. So once you complete this plastics injection filling evaluation and assessment, you move into core and cavity separation. So as a part of this core and cavity separation, so I'll be creating the core and cavity first, and then I'll be defining my parting line. So in this case, first we need to go for the pulling direction, and then we need to define all the edges first properly. In case if edges are not properly defined, say with respect to continuities, we need to work on that. So in this case, again, if there are any undercuts which are coming in, trims are coming in, or any ribs are coming in, we need to accordingly pick up our surfaces for the pulling direction. And then you need to define, as you can see on the right side, we have all the features to highlight, which is cavity, which is vertical, undercut, and then the associated faces. We need to define them here using this. Using this application, we are able to first pick up the pulling direction and then followed by the cavity surfaces. So you can also define the draft angle here in case if it is needed, and then you can highlight each and every any pockets or any cuts which are there. We need to highlight all those surfaces. Accordingly, we need to pick up the edges and things. So now you can see after doing this entire operation on this surface, you are able to see the core and cavity and also the pulling direction properly defined here. So this is like you have the engine cover and you are able to see how things are coming in. You are able to simulate also here in this workbench straight away. So this is a simple pulling direction which is defined here. Now I will go for parting line definition. So parting line definition has to be clear in this case. So this is the one which is going to decide the core and cavity separation. So the parting line definition has to be done here with the help of the edges which are available and which are also continuous in nature, typically tangent continuous in nature. So you pick up all the parting line elements here step by step, and then once you define the parting line, then you go for here we have the separation manager. You can highlight that, and now I need to go for, once I have the parting line in place, I can create the parting surface. So this parting surface can be created with the help of parting line by extrapolating the current surfaces which are available there. So we can extrapolate that in this way here. So I provide the direction which is tangent continuous and then which is also touching the parting line, and I'm able to extrapolate my surface to provide to create the parting surface first. So this parting surface creation is again very critical element here, because this is going to define the volume very clearly. So this is how the parting line is created. Parting surface is created step by step in this fashion. So once parting surface is created, now I am very much clear about my parting line, pulling direction and surface, and then the core and cavity separation. So this is what we are going to do this in this workbench, core and cavity separation workbench. And then once I complete my activity on this, then I can see the parting surface is properly defined with all its continuities in place for this particular component. So once this is defined, now I need to create the cooling circuit, the cooling lines basically. So we can simply make use of the sketch in a specific direction first, and we can impart this particular sketch onto the surface. So when you are imparting or projecting this particular lines, cooling lines, then they come on top of you can see here. So once you create these cooling lines, you can project them onto this particular surface and see how this cooling circuit is going to be in place. So I have a typical mode in base now. I'm just I have just created the bounding box, not just mold base. It is just a bounding box which is created based on the core and cavity definition which has been provided along with the parting surface in place. So now I will take this bounding box and then I will move into mold structure design. So this is the first next step. As I said, we have moved from plastic filling simulation and assessment, and then we moved into core and cavity separation workbench. We created parting lines, pulling directions, and parting surfaces. We have defined the core and cavity, and also we check the overall bounding box calculations and the volume calculations in this workbench. Now I move on to the conceptual design, which is basically dealing with the mold structure. So here I can choose mold base from the existing catalog. So in this case, there are multiple mold bases which are available with standard mold bases. It could be, Hasco or Futaba or MBE. There are several standard companies mold bases which are part of this particular library. You can bring those mold bases onto this particular bounding box calculations. And now in this case, we are creating these cooling lines, the cooling circuit basically. So we can simply create a sketch and then we can project this same sketch onto the cavity, onto the plastic, the engine cover plastic component. So onto the parting surface itself, you can project these lines and then create a cooling circuit. And you can verify and validate that. Once you complete the sketch, you can see this is being projected here. So the cooling lines are projected onto the parting surface here. Now you can also create the section for these cooling circuits. You can define the diameter of the the cooling lines, and then you can create those cooling lines here around the mold. Then once I complete that, then I will move into the next level, that is now I need to go and create baffles, and then I need to see how these baffles are connected with respect to the circuit. And then once I complete that, now I have this. I'm able to pick up all these from the catalog itself straight away, and then create these things, right? And I have these ejector pins highlighted over here. Again, the ejectors are sliders and lifters. You can see all the pins, core pins, ejector pins. These things can be defined from the catalog itself. These are all available within the workbench. So you need to pick up those and define them as per this mold design. Right. So once you complete that, so you have you can also check the interferences, and you can run through clash analysis and see how these ejector pins are highlighted over here. And also you can see them separately also in this tree structure, and you can see if any clashes are happening, we can actually eliminate them by running through the interference checks and analysis. So this is how I'm going to complete my mold structure design with respect to ejection systems or cooling circuit definitions, and then I will complete my mold structure design. Then I move on to the detailing of the mold base configurator, the detailed mold design in this example, in the same example. So here, as I said, we bring in this mold bases. In this case, we are picking up Hasco, which is the mold base, which we have selected here. DME, FCPK, Futaba. There are so many different standard mold bases which are available. You can pick up and position them here in a right way. So with respect to this mold design for the engine cover. So once you complete that, you will also look into all those sliders and lifters and the undercuts. You need to define them properly here. So we can look into again the tooling component systems, which is again picked up from the catalogs. So you can see here how the ejection is going to happen, and then without any rotation. So how the ejection is going to happen, that can be studied here. We can actually create the mechanism and run through that. So here, these are some of those cuts which are there. Now, accordingly, I need to pick up those elements and define those slides and lifters in this case. So again, the lifting mechanism also needs to be looked into. So how, once the core and cavity separation is happening, how this lifting mechanism happens, that can also be studied here in this. So on the, you can see in the tree structure, you have the mold base, injection system, ejection system, and also the runner systems. And then you have the complete definition of the detailed mold design, which is coming over here along with the mold base. Now, once I complete that, I can also look into the mechanism. We are defining the injection points here, as we defined in the earlier we did in the plastics filling simulations. Same way, I'm defining my injection points, and then I will run through the mechanism, and I'm creating a simple runner circuit with the help of a sketch. So for this injection points, I'm creating a runner, and then this is a simple sketch which can be utilized here, and we can create the runner as per the injection points. So once I complete this, my detailed mold design is ready, and now I can go for the complete mold mechanism. I can run through that and see how the lifting is happening, and then we can also create the mold drawing from this. So you can see the mechanism, a simple kinematics mechanism, which is running here. So this is how I'm going to create my mold structure design, and then detailed design, then followed by mold drawing. And if in case if any changes are happening, so how these changes have to be accommodated and automatically updated. So those are the things which are taken care in this 3D Experience platform interface, wherein you don't need to move, for all these multiple activities. Everything is done under one single user interface. So I will run through the full example here, whatever that we have discussed. So it will take you to the complete set of processes with respect to this detailed mold design of this engine cover. So we start with the plastic injection simulation. We see the temperature distribution, pressure distribution, shrinkage, and also what kind of ease of fill is happening, and we can see all those aspects with the help of business intelligence essentials. So we can also optimize the gate locations based on the simulation, and then now I move into the next level, that is the pulling direction definition. So we choose all the phases. Now there are so many phases which are being highlighted over here. So whether it is a primary pulling direction or secondary pulling direction, we can define all that with the help. Again, we can set up those draft angles and define this pulling direction. Then we enter into definition of parting lane. This parting line definition, again, we need to look into all those the complex shapes and undercuts, and then also any other elements. We need to look into that. So I create my core and cavity separation over here in this fashion. So these are all extracted surfaces from the parting lane. So I'm able to do that here. So we need to see that this parting line is fully continuous in nature, because this is going to help me to create parting surface as well later with the extrapolate commands. So once this is completed, then automated fill surface creation, and we run through one single command to create parting surface. So parting surface is generated in this fashion, right? Now, once I complete the parting surface, it looks like this. Then I create my bounding box and see how it is going to look like in this. My mold is going to look like. Then I define my cooling circuit. Basically, the cooling curves have to be created, and then these lines have to be projected onto the mold, and then you can see how they are being projected over here onto the core. So once it is completed, then I enter into drilled coolant based on the sketch, and then the baffle construction. So this baffle construction has to be defined over here, and then the ejection points, we need to look into that. We need to define the ejector pins, and also further all those rest of the elements, sliders and lifters. So these are all available. Once this is completed, then I will define my mold base. As I said, I pick up my standard mold base from the catalog, and then accordingly I will set it up over here with respect to this engine cover component. Then this is completed. Now I will also look into the mechanism, the ejector placement, and how they are being operated over here. So this ejector placement is all done here. We need to look at the anti-rotation detection in these ejectors, and then how it is going to lift this component outside. We can do the ejector kinematics. We can even reuse the complex lifters and sliders mechanisms over here, and then we can experience the entire design in motion. So from the mold base, you can see how this is being extracted out. The entire mechanism can be simulated in the same workbench. So this is how we complete this complete detailed mold design. Then I also create my injection points. Then I will also create a runner based on that injection points. So the runner gates are ready. Then you can see the final detailed mold design. Now I can go for mold drawing, basically the manufacturing drawing creation. I can definitely do that. So once I complete that, now I'm able to create my integrated bill of materials with respect to mold design. I can simply generate these reports and put them in the Excel sheet, and also you can also bring them into drawing as well. So this is how my complete detailed mold design is going to look like for an engine cover. So this is one case study I wanted to highlight in this demo today. So we can do all kinds of simulations. We can also, bring in all kinds of complex elements into this, and then we can define our detailed mold design in an accurate fashion. So the most important thing is that you are able to benefit, because this is all coming from the same user interface, and it is easier to define all the elements in one go. So, there are so many powerful assistants for core and cavity preparation, which is the most important activity of this mold design. And then you can also look at design change management, because if you make any small changes here and there, it can be automatically updated. And then, of course, we have the rich catalogs which are having all the standard mold bases, ejector pins, and then again sliders, lifters, and many other core elements of this mold design, which are readily available. And then, of course, you can also standardize, customize, and reuse these templates again for the other activities as well. And of course, you can always look for the quality improvement, and also you can reduce the total design cycle time, and you can ensure that there is a digital continuity and traceability secured with the parallel and all the downstream processes. So these are some of those benefits from this particular solution, because it combines all aspects, right from the surface creation to the parting line definition, pulling direction, then the core and cavity extraction, and also going with the mold structure design, all the elements, ejection points, as well as the cooling circuit definition and the cooling curve definition. And then when we complete all that, we will also move into generate these mechanisms, and we can also see all the interference clash analysis on the fly, and also we can arrive at an accurate detailed mold design in this fashion. So we can generate the drawings, you can also have the continuity, you can do all the modifications and automatic updates with the help of same workbench. So that's what I would like to offer here today with the help of this case study in this 1 hour of webinar. And yeah, here are some of those customers who have taken this solution and benefited from this. I have just highlighted a few of them from India operations perspective. And of course, globally also, like 3Con uses this particular solution. They're able to see the 50% improved design productivity. And apart from this, we also have SL Corporation from South Korea. So they also make use of this particular mold tooling design solution, mold tooling designer solution. And yeah, they are able to see a lot of benefits coming in. It's the much faster time in terms of design time, and also it's about accuracy, and also the right prediction that we can do using this. So it definitely serves in terms of quality improvements, design, reducing the design cycle times, and also the overall cost benefits that can come. So these are some of the examples I wanted to highlight today with respect to this particular webinar.
Yeah. So I would like to thank the audience for listening out our webinar and the technical presentation. I'm hopeful that they could gain much knowledge from this. In case of any other queries or any other mold tooling or mold design requirements, you can always reach out to us. Our contacts are displayed on the screen right now. You can note them down, you can mail us, or you can call us, and we'll be happy to address your queries. I would like to thank Shikumar sir and the audience once again. Thank you all.